In this video, we will talk about convergence of complex sequences and series. This is our overview slide, which we'll spend about 5 minutes going over before we go back and do each of these two topics in more detail and with examples. First, we will talk about sequences. So an infinite sequence, z1, z2 up to zn, and then that continues, of complex numbers has a limit z. If for each positive number epsilon, there exists a positive integer n naught such that the modulus of zn minus z is less than epsilon whenever n is greater than n naught. This is the picture that goes with the definition. So we're proposing z as our limit. And what we're saying is we can draw a circle, and it can be very small, arbitrarily small around z. The radius we'll call epsilon, and remember epsilon can be arbitrarily small. So as we look through our sequence of complex numbers, the numbers can bounce in and out of the circle. But eventually, once we surpass this index, n naught, so maybe n naught is out here somewhere, after this index, n naught, all of the rest of the sequence is going to be within the circle. In other words, all the zn, where n is greater than n naught, the distance to z is going to be less than epsilon. Again, in other words, it's in this circle. And since we can choose epsilon as small as we please, it follows that the point z naught becomes arbitrarily close to z as their subscripts increase. And then a limit z is unique if it exists. So when a limit exists, the sequence is said to converge to z, and we write the limit as n approaches infinity of z of n is equal to z. If a sequence has no limit, it diverges. And then last for sequences, we have this theorem. Suppose that zn is equal to x of n plus I y sub n, and z equals x plus I y. Then the limit as n approaches infinity of zn approaches z if and only if the real part approaches x. So the limit as n approaches infinity of xn equals x, and the limit as n approaches infinity of yn equals y. And I just rewrote that over here. The next thing we will look at are series. So an infinite series is a summation n equals 1 to infinity of some sequence. So summation n equals 1 to infinity z sub n is equal to z1 plus z2 up to zn, and it continues on. And it's a series of complex numbers converges to the sum s if the sequence of partial sums s sub capital N, which is the summation from n equals 1 to n, z sub n, which is equal to z1, z2, all the way up to z capital N, converges to s. Then we write the summation n equals 1 to infinity of zn is equal to capital S. When a series does not converge, we say it diverges. We have this theorem here. Suppose that zn is equal to xn plus iy, and capital S is equal to capital X plus I capital Y. Then the sum n equals 0 to infinity zn is equal to our capital S if and only if the sum for n equals 0 to infinity x of n is equal to capital X, and the sum from n equals 0 to infinity y sub n is equal to capital Y. We have this corollary. If a series of complex numbers converges, then the nth term converges to 0 as n tends to infinity. In other words, the sequence needs to be getting smaller. The terms of convergent series are bounded. That is, there exists a positive constant m such that the modulus of zn is less than or equal to m. A series is said to be absolutely convergent, which is a stricter form of convergence, if the series, the summation of the absolute values of zn, which is defined as square root of x to the n squared plus y to the n squared, converges. And again, the absolute convergence of a series of complex numbers implies convergence of the series, because absolute convergence is a stricter form of convergence than just regular convergence. That concludes our overview, so now we can go back and take a closer look at sequences. We will take another look at the definition of the limit of an infinite sequence. So an infinite sequence, z1, z2, up to zn, and then it continues, of complex numbers has a limit z if for each positive number epsilon there exists a positive integer n naught, such that the distance between zn minus z is going to be less than epsilon whenever n is greater than n naught. And here is a more detailed picture than what I gave in the overview. So the idea is that we're going to identify this z as our limit. And it says we can choose a positive number epsilon as our radius around z. I actually don't like this red. I'm going to get rid of the red. And we can take this epsilon arbitrarily small. For now, we're just going to use epsilon of this value here. Then we have our sequence of numbers. Let's look at z1, which is outside the circle of radius epsilon, z2, which is inside, z3, which is outside, z4, which is getting closer but still outside, z5 is inside, z6 is outside. Then we have z7, it's inside, z8 is inside, and after that maybe z9, z10, and all the other z sub n's are inside the circle of radius epsilon. In that case, that would imply that z is a limit. Our positive n naught, where everything starts being inside the circle, in this example would be n naught is equal to 7, because whenever n is greater than n naught, then our z sub 7, z sub 8, z sub 9, we said all the other z sub n's are within the circle. Again, z sub n minus z, so the distance between z sub n and z is less than epsilon, meaning it's inside the circle. This is totally analogous to how we defined limits of infinite sequence in first year calculus when we had x as our real number line. And if we wanted to propose x was our limit, then we would look at an interval around x plus epsilon, x minus epsilon, I'm missing an epsilon here, and maybe this is where I graph my x1, x2, x3, x4, x5, x6, x7, x8 up to xn. So maybe x1 is outside of our kind of range. x2 might be inside, x3 might be outside, x4 is outside, x5 starts to be inside, x6 jumps out. But eventually x7, x8, and all the other x's start to be within our boundary of epsilon, which would make x our limit, except I shouldn't say it's automatically our limit. The other condition is we need to be able to make epsilon arbitrarily small. In our example here in the complex plane, maybe now I want to make epsilon this green radius, so then I have this circle of a smaller radius. So now my z7 is outside my circle, but that's okay because now my integer n naught could be z8. And then everything after z8 might be in this green circle. So if I can keep making my epsilon smaller and smaller, and I might have to get bigger and bigger n naughts, but eventually I'll be able to find an n naught such that any index greater than n naught stays within the circle. So that's what makes it a limit. And that's the second point here. Since we can choose epsilon as small as we please, it follows all the points z naught become arbitrarily close to z as their subscripts increase. And the next thing we need to know, when a limit exists, then it's going to be unique. So when a limit exists, the sequence is said to converge to z, and we write the limit as n approaches infinity of z of n is equal to z. And if a sequence has no limit, we say it diverges. And last, we have this theorem here that puts our limits and our convergence in terms of real numbers. That is, suppose that Zn can be decomposed into xn plus I yn. So now we have xn, a sequence of real numbers, and yn, a sequence of real numbers. And we have another complex number z, that's going to be our limit, is equal to x plus iy. Then the limit as n approaches infinity of Zn is equal to z if and only if the limit as n approaches infinity of xn equals x, and the limit as n approaches infinity of yn equals y. And I just rewrote this all in handwriting just because I like the look of this. For our first example, What value does the sequence Zn equals 1 over n cubed plus I converge to? So I can write the limit as n approaches infinity of 1 over n cubed plus I. Now using our theorem here, so we're looking for the limit as n approaches infinity of x of n, which is equal to 1 over n cubed, plus I times y of n, which is equal to 1. And by our theorem, this is going to be the limit as n approaches infinity of 1 over n cubed, that's this portion here, plus I times the limit as n approaches infinity of 1. As n approaches infinity, 1 over n cubed is going to be equal to 0, and this is I times, well, the limit as n approaches infinity of 1 is still 1, so our final answer is I. One other note, and this is important, for each epsilon greater than 0, so when someone gives you an epsilon, we can compute n. So we'll do that for this example here. We are going to start with this condition here, which I will circle in yellow. So we want the absolute value of Zn minus Z to be less than epsilon. And now I have Zn minus Z. So here we calculated the limit Z is equal to I. We have the formula for Zn is equal to 1 over n cubed plus I. So this converts to 1 over n cubed. The absolute value is equal to 1 over n cubed, and we want this less than epsilon. So here is our equation for calculating n. In other words, n has to be greater than 1 over the cube root of epsilon. Our second example is what value does the sequence Zn equals negative 2 plus I times negative 1 to the n divided by n squared converge to? First, I'm just going to rewrite this as the limit as n approaches infinity of Zn is equal to the limit as n approaches infinity of negative 2 plus I, negative 1 to the n over n squared. Again, now using our theorem over here, where xn is equal to negative 2 and our yn is our negative 1 over n squared, this is equal to the limit as n approaches infinity of xn, which is negative 2, plus I times the limit as n approaches infinity of yn, which is negative 1 to the n over n squared. So the limit as n approaches infinity of negative 2 is just negative 2. The limit as n approaches infinity of negative 1 over n squared, this n squared dominates, so this goes to 0. So our answer is negative 2. I also have this drawn out another way. Here we have our x of n. This is our sequence of just negative 2, negative 2, negative 2 forever. Our y sub n is our sequence for when n is equal to 1, that would be negative 1 over 1, which is minus 1. When n is equal to 2, this is going to be positive 1 over 2 squared, which is 1/4. Then we have minus 1 over 3 squared, which is 9. Then we have a positive 1 over 4 squared, which is 16. So you can see this series getting smaller and smaller. Although it does bounce around between negative and positive, it keeps getting smaller and tends towards 0, whereas this series is going towards negative 2. And essentially what this theorem says, and exactly what we computed here, is we can analyze the real part separate from the imaginary part and then add them together at the end. There is something interesting if we use polar coordinates. In other words, Rn, the radius, is equal to the magnitude of Zn, the distance from the origin. And our theta n, our principal argument of Zn, is going to be between negative pi and pi. To calculate our radius, or the limit as n approaches infinity of our radius, looking over here at our z to the n, the radius then is going to be our x term squared plus our y term squared, all square rooted. So our x term is negative 2, squared is 4. Our y term is negative 1 to the n over n squared. When we square this, this becomes positive over n to the 4th, and then we square root the whole thing. So the limit as n approaches infinity, this goes to 0, and we're left with square root of 4, which is equal to 2. So the limit as n approaches infinity of Rn is not a problem. It's equal to 2 in this example. The problem comes with our theta. So if n is even, so z to the 2n, and I'm just going to put the 2 in front of the n to emphasize it's an even number. Our Zn is going to look like our negative 2 plus I. Since this n is even, our negative 1 to the n becomes positive, and then we have our n squared. What this looks like in the complex plane, we have the negative 2. So on the x-axis, we have a negative 2. On the y-axis, we have some positive number. So we're going to be over here in the second quadrant. And as we increase, we're going to get, as theta increases, we're going to get closer and closer till finally we get to negative 2. As n approaches infinity, this becomes 0, and we get to negative 2. But we're coming around this way, which means our theta is going to equal to pi when we have an even n. We're going to contrast this if n is odd. So z to the 2n minus 1. I'm just writing this as this form to emphasize it's an odd number. Again, our x-coordinate is 2, but now our y-coordinate, this is going to be a negative 1 over n squared. So it's going to be, x is positive, but our y is negative. So we're going to be over here in the third quadrant. And as we get closer, as n approaches infinity and this becomes 0, we get closer to negative 2, but we're coming at it from this direction, which means our theta is going to be negative pi. And that means we have two different limits. So the limit of theta n does not exist as n approaches infinity when we're using polar coordinates on this example. That covers our topic of infinite sequences, so now we're ready to look at infinite series. An infinite series is a summation n equals 1 to infinity of Zn, and it's equal to Z1, Z2, up to Zn, and then it continues on into infinity, of complex numbers converges to the sum S if the sequence of partial sums, and the partial sums is the sum from n equals 1 to n, this capital N here, of Zn, which is equal to Z1, Z2, all the way up to Zn, and then it stops. If this sequence of partial sums converges to S, then we write the summation of n equals 1 to infinity Zn converges or is equal to S. You can see then how convergence of an infinite series is defined in terms of convergence of a sequence of partial sums, and we talked about convergence of sequences just a few minutes ago. And it is in this way that we relate these series to a sequence of partial sums. And from that relation, we have this theorem, which is totally analogous to the theorem we have for sequences. So suppose we have our sequence Zn, which is equal to the sequence xn of real numbers plus I times sequence of yn of real numbers. And then capital S is equal to capital X, a real number, plus I times capital Y, another real number. Then the series n equals 0 to infinity Zn equals S, if and only if the series n equals 0 to infinity x of n is equal to x, and the series n equals 0 to infinity y of n equals y. For your reference, I put that analogous theorem for sequences over here. We have the corollary. If a series of complex number converges, then the nth term converges to 0 as n tends to infinity. And if we look at that, what that means is eventually somewhere out here, our z sub n's need to start getting smaller and tend towards 0. Our next fact is the terms of a convergent series are bounded. That is, there exists a positive constant m, a maximum, such that the absolute values of Zn are all less than or equal to m. We have absolute convergence, which is a more strict form than just regular convergence. So a series is said to absolutely converge if the series n equals 1 to infinity of modulus of Zn, where modulus of Zn is defined as the square root of x of n squared plus y sub n squared. So if the series of absolute values converges, we call that absolute convergence. And we have the corollary: the absolute convergence of a series of complex numbers implies the convergence of the series. Again, absolute convergence is a more strict form, so if you have absolute convergence, you have regular convergence as well. And last, we have this theorem: a series converges to a number s if and only if the sequence of remainders p sub capital N is equal to s minus s sub capital N tends to 0. We can use this in an example problem. We'll use the remainders to verify that the infinite series n equals 0 to infinity zn is equal to 1 divided by 1 minus z when the modulus of z is less than 1. And we're also going to use this identity here. 1 plus z squared up to zn is equal to 1 minus z to the n plus 1 divided by 1 minus z when z is not equal to 1. We will start by looking at the sequence of partial sums, our S capital N. So we're going to look at the series from n equals 0 to n equals n minus 1 of Zn. When we expand this out, we get 1 plus z squared up to Zn minus 1, which, using this identity here, is equal to 1 minus z to the n divided by 1 over z. If S of z, which is our infinite series, is equal to 1 divided by 1 minus z, which is our hypothesis over here, then our remainder is equal to S of z minus Sn of z, which is equal to 1 over 1 minus z minus, over here, 1 minus z to the n over 1 minus z, which is equal to z to the n over 1 minus z when z is not equal to 1. Which means the absolute value, the modulus of Pn of z, is equal to the modulus of z of n divided by 1 minus z, which, if z is less than 1, will tend to 0. By our theorem here, the p sub n tending to 0, if and only if, so reading it the other way, means that our series converges to S. To review what we have covered in this video, we looked at convergence of sequences in series. First, we defined an infinite sequence, z1, z2, up to zn, and then continuing on to infinity, of complex numbers have a limit z if for each positive epsilon there exists a positive integer n naught such that the distance between zn and z is less than epsilon whenever n is greater than n naught. And this was our picture. The idea is we have a sequence of complex numbers, so z naught, z1, z2, up to zn, and they approach this number here, this complex number z. And if it approaches z, then we can take epsilon arbitrarily small, and at some point there will be an n naught in this sequence, such that any index greater than n naught, so z of n naught and anything greater, will all be within our radius of epsilon. No matter how small we choose, we can always find an n naught. If we do have a limit z, if it exists, then the limit is unique. So a limit is unique if it exists, and when a limit exists, the sequence is said to converge to z, and we write the limit as n approaches infinity of zn is equal to z. If a sequence has no limit, we say it diverges. And then we have this other convenient theorem for determining the limit. Suppose that we have a sequence of complex numbers zn, which is equal to a sequence xn plus I times a sequence yn, where xn and yn are sequences of real numbers. And z is another complex number equal to x plus iy, which we will assume will be our limit. Then the limit as n approaches infinity of zn is equal to z if and only if the limit as n approaches infinity of xn equals x, and the limit as n approaches infinity of yn equals y. And I rewrote that over here. The next topic we talked about was an infinite series, which is a summation of a sequence zn, which is equal to z1 plus z2 up to zn, and then plus, and it continues on to infinity, of complex numbers, and we say it converges to the sum s if the sequence of partial sums, that's S of n, that is the summation from n equals 1 to n, Zn, which is equal to Z1, Z2 up to Zn, converges to S. And then we write the infinite series n equals 1 to infinity, Zn is equal to S. When a series does not converge, we say it diverges. And in this way, we define the convergence of our infinite series in terms of convergence of a sequence of partial sums. So they're definitely related. And then because we have this theorem, we have the corresponding theorem for series, which is suppose that we have a sequence Zn, which is equal to a sequence Xn plus I, Yn, and S is our sum that we're guessing or proposing is what Zn, the summation of Zn converges to, and S is equal to X, a real number, plus I, Y, a real number. Then the summation of Zn equals S if and only if the summation from n equals 0 to infinity Xn equals capital X, and summation from n equals infinity of Yn equals capital Y. We have this corollary: if a sequence of complex numbers converges, then the nth term converges to 0 as n tends to infinity. And we also have the terms of a convergent series are bounded, that is, there exists a positive constant m such that the absolute value of Zn is less than or equal to m for all n. We have the definition of absolute convergence. So a series is said to be absolute convergent if the series of the absolute value of Zn converges. And the corollary is the absolute convergence of a series of complex numbers implies the convergence of the series. And finally, a series converges to a number S if and only if the sequence of remainders, which is denoted Pn, which is equal to S, our sum that we converge to, minus Sn, our partial sums, tends to 0. And that's it for this video. Thank you for watching.